chapter 8. So we were talking about the Bohr atom. A Bohr atom, we have these orbits. They're forbidden orbits and allowed orbits. So the model is something like this, where have the first orbit here, n equals 1. Second orbit, third orbit, fourth orbit. Although this is not to scale because the distance, you see, we look at it, the first orbit is, if it's given by A naught, which is about 53, 54 angstroms. Then the second one is, actually you'll see the pattern, it's n squared A naught, or n squared R, or actually R1, R0, excuse me. Then it goes on, so 4, 9, 16. That's the model. And then when a hydrogen atom absorbs or emits light, what happens is we have transitions between these. And the energies can be figured out from physics here. The energy of each orbit is given by this equation, where R sub h is the Rydberg constant. N is the allowed energy level. R sub h has the energy of 2.179 times 10 to the minus 18 joules. 2.179 times 10 to the minus 18 joules, how much coffee can you warm up with that many joules? You know, is that gonna warm up a cup of coffee? No, but you know, this amount of energy, we have two different contexts. You know, the energies that we dealt with in chapter 7, you're looking at large quantities, kilojoules. When we're dealing with single atoms, this is a large quantity of energy. You know what 2.179 times 10 to the minus 18 joules can do? That can knock an electron off a hydrogen atom completely. Because when we look at the energy states, this is what we can get from it, because we can calculate. Well, how can we calculate? You know, the first allowed energy state is E1, n equals 1. That's here. Well, E1 is pretty easy because the energy for this state is just equal to minus R sub h, which is 2.179 times 10 minus 18 joules divided by n squared. So it's just equal to minus R sub h. And then we go to the highest energy. The highest energy is E infinity. E infinity here, and then E infinity is going to have an energy of what? Well, minus R sub h over n squared. When we plug in infinities, we're going to get 0. And so basically the highest energy is 0 joules, and that's defined as, well, how far away is the electron from the nucleus? And so if we look at the orbit, it's going to be in the n equals infinity orbit. The n equals infinity orbit is going to have a radius, r, of n squared times a naught, where a naught is, let me just get that for, it's 53 or 54 angstroms. Here, 0.53 angstroms, or 53 picometers here. A naught is 53 picometers. And so what is it? Well, you know, it's infinite. Basically, it's infinitely far away. Infinitely far away just means, well, what does that mean? For an electron to be infinitely far? Well, it means it's completely out of the influence of the proton anymore. And so what we call this electron is, we call an ionized electron. Ionized means it's just been ripped off the hydrogen atom completely. So we knock it off. And so the 0 point here, is this an arbitrary 0 or an absolute 0? What do you think about this 0? This is an arbitrary 0. And so it's just arbitrarily defined. The 0 of energy, is it really 0 energy? A proton has no energy, an electron has no energy? No, because when we think about it, you know, there's kinetic and potential energy, it's total energy. And so this is a completely arbitrary 0, but it's all we're doing is we're looking at electron energies in the hydrogen atom, and so this is why we can do this. And so this energy state, this highest energy state, right, is the is what we define as 0, and that's when the proton and electron are completely separated. Now, when you bring the electron closer to the nucleus, what happens? When you bring the electron closer to the nucleus, then the energy goes down. So this is why we have negative energies here, because the way this looks in terms of energy versus radius is, if an electron out here is at infinite distance, then it's 0 energy. But as it gets closer and closer, then the energy of that goes down. Something like this. And so this is what we call a potential energy well. You know, the energy drops down until it hits this minimum here. And that minimum is, you know, as close to the nucleus as it can get. But you really, the minimum energy is when it goes into the nucleus. And so why doesn't the, you know, at the first orbit here, the first orbit here, and the electron's here, and it's orbiting at what radius? Well, the radius is equal to n squared a naught. And so the first orbit is at 53 picometers. At 53 picometers, that's an allowed orbit. This is an n equals 1 orbit. Now, why can't the electron, can the electron orbit at 52 picometers? Is that allowed or forbidden? It's forbidden. And so one of the questions that came up is, why doesn't the electron just get closer and closer to the nucleus? There's an electrical attraction here. And the answer is, it's forbidden. And so then the next question is, why is it forbidden? Why is it forbidden? What makes it forbidden? Is there a wall, impenetrable wall, or some invisible shield that prevents it from getting closer to the nucleus and getting farther from the nucleus? And then the answer is no, because it's empty space. So then why is it forbidden? Does somebody have the answer? You want to come up with some hypothesis for me? Test it with some experiments? This is very simple. So somebody might ask you, why is it forbidden? Just explain it to me. And what would you tell them? Likewise, it can't orbit out farther. It can't go to 54 picometers. Why? Well, this gets into maybe some philosophy behind science. Science really doesn't explain why. Science is just a description of nature. And this is how nature behaves. Why it doesn't happen? It just doesn't happen. And these are things that are called the postulates of, have you heard of a postulate? Postulate of quantum mechanics is you just take it without proof, because this is how nature is observed to behave, and scientists are just taking observations of nature, right? And so if the electron doesn't spiral, because it can't, it doesn't. You know, that's observed. Well, unfortunately, well, you know what we can do is we can calculate. If an electron were here, and it gets promoted up to here, what have we done? Well, you know, this is called the ionization energy. So how much is the ionization energy of hydrogen? Well, we just calculate delta E. Delta E is equal to E final minus E initial. E final is up here. You know, that's E final is 0 joules, right? E initial is down here. That's a minus 2.179 times 10 to the minus 18 joules. Then we get plus 2.179 times 10 to the minus 18 joules. So how much can you do with 10 to the minus 18 joules? You can do a lot. You can knock an electron off to infinity on a hydrogen atom. Although it seems like an exceedingly small amount of energy, it's a lot. The reason it seems like an exceedingly small amount of energy is because we don't deal with single atoms usually. You know, single atoms, instead we deal with how many atoms? We usually deal with moles of atoms. And so what we say is this is joules per atom, even though it's not written there. If we wanted to figure out how many joules per mole of atoms, we'd have to take this number and multiply by Avogadro's number. It says 2.179 times 10 to the minus 18 joules per atom. And then we know that there's 6.022 times 10 to the 23rd atoms per mole, and that gives us how many joules per mole. Can somebody calculate this? Or here, maybe I can do it on Excel. Or actually, I have a calculator here. I'm good on my calculator. So 2.179, although this is not a scientific, but 2.179 times 6.022. We'll do the exponent later, 13.12. 13.12, and then 18 and 23 gives us 5 times 10 to the 5th joules per mole. So let's do that to 10 to the 3rd. So 1312 joules per mole. So this gives us 1,312 kilojoules per mole. And so we have two energies that we're dealing with here, the energy per atom and the energy per mole here. This is important. And so let's do another calculation here. Let's look at the relationship between photon energy and total energy. And we're going to backtrack a little bit and we'll take actually we're going to jump ahead and then backtrack. Jump ahead to chapter 10. We can use photons to break bonds. So for example, here, to break a hydrogen-hydrogen bond would require 435.93 kilojoules per mole. So let's try to break a hydrogen-hydrogen bond. We're using a photon. And so what I'm going to ask you is this: what wavelength of light is required to break a hydrogen-hydrogen bond with an energy of 435.93 kilojoules per mole. So people dig around and they look. One of the equations is E is equal to H nu, which is equal to HC over lambda. And so we can solve for lambda. Lambda is equal to HC over E. And so I have my energy here. And so I plug it in. H is Planck's constant, 6.626 times 10 to the minus 34. The units on H are very interesting. It's joules per times seconds, not joules per second. A joule per second would be a watt, but a joule times a second, this is called a unit of action. Joules times seconds. Times 2.998 times 10 to the 8 meters per second, divided by the energy, 435.93 kilojoules. A lot of people do this. Let me just do 435.93 kilojoules. And then we've got to convert it to joules. Let's go ahead and convert it to joules down here, 1,000 joules per kilojoule. Usually when we do this, though, we usually take the absolute value of energy. Because, if it's exothermic or endothermic, what we do is we say that light is being emitted or light is being absorbed, but it's a positive amount of energy. And so it makes no sense to have a negative wavelength. Negative wavelength doesn't give you a negative photon. Well, anyway, going back to this, do you see something wrong? I did something terribly wrong. Do you see what I did that's terribly wrong? What I did that was terribly wrong is I'm calculating the energy for a single photon. And so the setup here is a single photon breaks a mole of bond. A single photon breaks a mole of bonds. Is that going to happen? So I'm going to get a ridiculously small wavelength. And so let's go ahead and calculate the wavelength here. What would the wavelength be for this? Let me get my calculator out here. So 6.626 times 2.998 divided by 435.93 divided by 1,000 equals 4.557 times 10 to the negative fifth. 4.557. I have to do one more thing. 4.557 times 10 to the negative fifth. This is not a scientific calculator. I'm going to multiply this times 1 times 10 to the minus 34 and 8 would be minus 26. Minus 26, and then add these together. 4.557 times 10 to the minus 31 meters. Okay, then I just go, okay, what kind of light is that? What kind of light is this? 4.557 times 10 to the minus 31 meters. That sounds reasonable, doesn't it? Does any kind of alarm bell go off in your head when you look at that number? Or does that seem like, yeah, it could be? Any kind of alarm bell go off in your head? Probably no alarm bell goes off in your head, and that's why so many people can get this wrong, and so many people do get this wrong, this particular problem, because they don't see that that's a ridiculous number. Why don't they see that's a ridiculous? Because they don't know the range of wavelengths for light. I told you to memorize the range for visible light, right? But I never told you to look at the range for the electromagnetic spectrum. And so let's take a look at the range for the electromagnetic spectrum. When we look at the range for electromagnetic spectrum, it ranges from radio waves with wavelengths of about 10,000 meters, or 10 kilometers. Wavelength 10 kilometers on the long side. On the short side, what are the shortest wavelengths that you see? 10 to the minus 16. 10 to the minus 16 would be gamma rays. Well, 10 to the minus 16, that's like 15 orders of magnitude smaller. What kind of light is that? And so that's like going from, 10 to the minus 16 to 0. And so we're spanning this kind of range, right? And so we got to go this kind of range smaller. What kind of light is that? Yeah, this is enough energy here with this wavelength to completely annihilate the atom, right? I don't know what it would be destroyed to, but if you punch that much energy into a single photon, and what do we say? We say there's something called quantum Stoichiometry. What's the quantum stoichiometry? This is something I talked about on Thursday. Quantum stoichiometry. Quantum stoichiometry is just this. It's just a single photon cannot break a mole. You can't just throw, I'm going to throw one baseball and hit everybody in the stadium. Is that going to happen? No. A single baseball ball will hit one person, right? And that's the way it works. A single photon will break one bond. It's not going to break an Avogadro's numbers worth of bond. If it can, then that's what we would call this is the end of the world photon, basically, right? It's just going to destroy the planet.
So,
Mm-hmm.
is when a single proton only brings one bond?
Yes. A single photon will promote one electron. I can't promote it. Let's say I can't promote a mole of electrons with a single photon. Yeah. That's what I talked about on Thursday. Well, getting back to this is why it's so important. A lot of people say, I don't need to memorize, I'll just Google it. But, you know, I was at a conference, you know, in the chemical engineering department at UCSD. And there's this guy, Henry Weinberg, who's super famous chemical engineer. That many, many years he was at Caltech, and then they brought him to UCSD. And there's a person giving a talk about energies, and unfortunately they didn't quite have the. Anyway, it was some kind of ridiculous amount of energy that they were saying, and it was pretty embarrassing. But it's good to have some kinds of things to memorize, you know. But you know, most people don't memorize that because this looks reasonable. We get scientific notations all the time. So how do I fix this problem? How I fix this problem is I don't forget the units. You know, a lot of people just, and sometimes we're all guilty of this. We leave off the units because, you know, on equations we don't write it because when we have the equation there, it's always kilojoules per mole of reactant or product, right? Per moles, whatever it's specified. But this is kilojoules per mole of hydrogen molecules. What we need to do are HH bonds. What we need to do is we need to figure out how much energy per bond. And so when we do that per bond, then we know that in a mole of hydrogen, there are 6.022 times 10 to the 23rd bonds. And this is going to give us a lot less energy required to break that. So we'll just calculate that. 453.93 divided by 6.022. Well, so I wonder if there's a scientific calculator. Probably online. You use that. 75.37. So we'll just go 4.6. Actually, we're more. We're allowed 4.6 big. 75.378 times 10 to the minus 23. And so, you know, we'll just leave it. We'll go 7.5378. So the 8 times 10 to the minus. Make this smaller. We'll make this bigger. So times 10 to the minus 20. Small. 4. Is that right? No, 22. Joules per hydrogen atom or molecule. Actually, I don't need to change it. I'll just leave it. No reason to change it. Hydrogen molecule. All right, now when we plug that in, lambda is equal to hc over E, and we're going to get this. let's go ahead and recalculate it. So I'll recalculate this number here, and I'm going to get, just do it. Just take that number and divide it. I'm just going to take that number and divide by Avogadro's. It's going to save me time. So 4.557 divided by 6.422. The only thing is I'm going to get round off error. That's all right. 0.756. 0.756. 75672 times, okay, we did Avogadro's, so Avogadro's would be divided by 10 to the 23rd, so 31 would be 7, 8, 10 to the minus 8. And so let's do it, we're going to get 7.5672 times 10 to the minus 9 meters. Why did I pick minus 9? Do you know what minus 9 is? Minus 9 is called a nano. This is a nanometer. This is 7.5672 nanometers. This one, you should know where it is. Where is this one in terms of light? Ultraviolet. And so it takes UV light to break a hydrogen-hydrogen bond. We don't need X-rays or gamma rays. We certainly don't need an end-of-the-world photon to do it. All right, so that's reasonable. So that wavelength is required. All right, let's go back to this. And so the Bohr model, what was the problem with the Bohr model? Bohr model has lots of nice diagrams right here. Do you see? If we go from the n equals 1, 2, 3, the n equals 3 to the n equals 2, you know, if we have this transition, it emits red. If we go from 3 to 2, it emits blue. 4 to 2 emits, and then these ones, like a 2 to 1 emits infrared, and let's say a 3 to 1 emits UV. And so we'll see lines in the infrared and the UV. And so this seems to look pretty good, except there's one major problem. What's the major problem with this model? Oh, they also give names to these historical. So, for example, the visible were observed by Balmer. So they're named the Balmer series, the red, green, blue, and violet. There are 4 lines here. They didn't write the 4th one. 4th one's the violet. Then the UV weren't observed until much later because you know, they're invisible. And so UV named after Lyman. And then the infrared was named after some other guy. You don't have to know the names for these, but there are lines in the infrared. These are experimental facts, right? These observations are factual observations. But unfortunately, these factual observations, well, the theory, what is the theory supposed to do? The theory is supposed to give you a fundamental picture, right? And it does. You know, the Bohr theory gives us a fundamental picture. The things, the orbits, and electrons are in these orbits, etc. But the theory is also supposed to do one other thing. What is this theory supposed to do? The explanation is the fundamental picture. The theory is supposed to be, well, this is all the way back in week 1, so it's a long time ago, probably long forgotten. Theory is supposed to do 2 things. Actually, I said it more than once. I said it multiple times throughout the semester. Predict. And that's what Bohr couldn't do. Bohr could not predict the next one. The next spectrum was the helium, right? And unfortunately, this model failed. So the facts are there, but the theory failed, and so unfortunately, the theory is wrong. Usually theory is, widely accepted. Well, it was widely accepted because it seemed to work until they got to something like this. You look at all these lines here. Look at all these lines. This is an emission mode where it emits lights. This is an absorption mode where you shine the rainbow and see what colors are missing. It's absorption spectroscopy, emission spectroscopy. And it's just either going up or down. Here's the ionization of the hydrogen atom. We just did that calculation. All right, so what do you do? If the theory fails, you got to come up with a new theory, right? And so how do you come up with new theories? Well, maybe come up with a new hypothesis. You could come up with a new hypothesis. What's your new hypothesis for the helium atom? Come up with a new hypothesis for me. Were there competing hypotheses at this time? There was competing hypotheses at the time of the Rutherford atom because there's the nuclear atom model and the plum pudding model. So if the nuclear atom fails, at least you have the plum pudding to fall back on. But was there an alternate hypothesis here during Bohr's time? Did somebody come up with an alternate hypothesis? No. And so what happened? Well, Bohr is obviously wrong, so what do you have to do? Okay. Well, we've got to come up with a new hypothesis, but how can we come up with a new hypothesis? Well, what you usually do is, if this fails, then you just take more observations. Well, there are two things that, two ideas, this is section 8-5, two ideas leading to the new quantum mechanics. And so not everything of Bohr was thrown out. This whole idea of quantized energy levels is still in effect. But the two ideas leading to the new quantum mechanics is this guy, de Broglie. De Broglie came up with this. His startling proposition was that small particles of matter may at times display wave-like properties. And so how did he come up with it? Well, you can read through that here. But basically there's wave-particle duality for light. Light has particle-like properties. That is, we have these things called photons of light. Photons aren't a true particle in the sense that, they have a rest mass. They have mass. They don't have mass. In this, the wave-particle duality, what de Broglie is saying is that all particles have wave properties too, wave properties like light. The wavelength of it is given by this famous equation here. So these are the two ideas. One is this de Broglie. This is for matter. This is not for light. And the de Broglie wavelength for matter is given by h over p. P is called momentum, but we're not going to use it. We're going to just do h over mass and u. U is the velocity. And so it's h, which is Planck's constant, over the mass of the particle times its velocity. All right, and so what this means is that if we are looking at a massive object, you know, if we're looking at a massive object, the mass is huge. If mass is huge, then the wavelength is exceedingly small. What happens though, you know, when matter interacts with wavelengths, you can think of it in a both sense as well. We're going to think of it in two senses, in the sense of something called the standing wave and in the sense of a boat or a buoy. You know, if you look at a little buoy in the ocean, let's say, you have a buoy in the ocean and the waves are coming by, right? And this buoy is going to be moving up and it's going to be moving down with the ocean waves coming by, correct? And so here the wavelength is on the order of the size of the buoy, let's say. But let's say, you know, this exact same wave here, there's a container ship here. You know, and for the container ship, the wavelength is very small compared to the size of the container ship. And so do you think this container ship is going to be moving and oscillating like this buoy is in this? No. Not at all. Oh, there's another way of thinking about this as well. When the wavelength is much bigger than the particle itself. But we'll look at that later. Well, how does this impact us? Well, the way this impacts us is this. If we think about a particle that's confined in a box, like this. There's a particle in a box. When the wavelength approaches the size of the box, then the wavelength is going to have a significant impact on the energy. And so let's say we confine a particle in a box and we have something called a standing wave. This would be like a guitar string. Actually, that's the other analogy, the guitar string analogy. We'll just look at a guitar string. We see that energy is quantized here. You know, energy is quantized. It's going to be n times 1/2 of wavelength, 1/2 of lambda. And so if we pluck the string, we could get a half wavelength in there. If we plug it a little harder, can we get like a little bit more than a half a wavelength? Maybe just a fraction more than a half a wavelength? No. If we plug it harder, the next allowed, I guess, tone for this would be 2 half wavelengths. But everything between a half a wavelength and 2 half wavelengths is forbidden, right? Because it just wouldn't work on a standing wave. The next one that's allowed is 3 half wavelengths. And so we see this quantization for standing waves like this for musical instruments. Let me look for this diagram here. And so the first allowed energy is this, and then this is going to be a little higher in energy, but any energy between these two is going to be forbidden. And the next allowed would be 3 half wavelengths here, 4 half wavelengths, etc. Okay, when we get to very high energies, at very high energy, this is what it looks like. Let's go to, what's that? 1 million, billion, trillion? No, billion? 1 billion? Okay. After 1 billion, what's the next allowed N value? The next allowed N value would be N equals 1 billion and 1. Now, is there going to be a significant energy difference between 1 billion and 1 billion and 1? Are you going to really notice the tone difference there for the instrument? No. In fact, the next allowed energy is right on top of it. So let's do that. Here. Like this. What's the next allowed energy? And what's the next allowed energy after that? 1 billion and 2. 1 billion and 2 is barely any higher. In fact, it's pretty much just overlapping 1 billion and 1. And so what happens is this. When the wavelength is small compared to the dimensions, then the wavelength doesn't have a huge impact on the energies here. When the wavelength is about the size or the dimensions of the object, then it has a significant impact because the next allowed one is going to be much higher in energy here. And so this is what we have. And so the analogy here would be to confine an electron. If you confine an electron in a big box, then if you confine an electron in a big box, then the wavelength doesn't have much impact. Because the box is big, wavelength is small, therefore the energies are tightly spaced like this. An electron in a big box would be like a chunk of iron or a tungsten filament in a light bulb. If you have a chunk of iron here, like an iron bar, if you have an iron bar, then this electron, is going to have wavelengths, and the wavelengths are going to be small compared to the bar, such that, when we excite that wavelength, we can excite a little bit. If we excite it just a little bit, a hair more, or we could excite it a lot, way up here. And we could excite it everywhere in between because what we have is what we call a band of allowed energies. A band of allowed energies. And so this is why a chunk of metal, was like a black body. It's a black body because when we're looking at this, the next allowed one is just the hair above. In fact, this allowed energies are so tightly spaced, it's pretty much a continuum. And so in other words, a continuous band of energies. Whereas if we were to look at a single iron atom, a single iron atom is not a black body emitter. A single iron atom is going to have a line spectrum. And so over here what we'll have is we'll have the continuous band of allowed energies. So this would be the spectrum here for the metal. And so we see a black body. When we go to an iron atom, what we see is we see a line spectrum. There are distinct allowed and forbidden energies. And so why is that? Well, why that is because if we have an electron in an atom, say we have an iron atom here. We have an electron in an iron atom. It's like a scaling wave. This electron's confined to the iron, whereas in iron metal, it's not. Well, we'll leave it at that. And so what has to happen is this. If the wavelength is offset a little bit, what happens is eventually the peaks and the valleys coincide. And when a peak and a valley coincides, we call that destructive interference. And so if these wavelengths are offset just a little bit, we have destructive interference of the wave. And the wave cancels itself out because the peak will coincide with the valley. And it could just be offset a little bit because eventually it'll just completely cancel. And so what we have to have is we have to have a constructive interference. That is where we have an integral number of half wavelengths. And so let's say here we have 4 half wavelengths, so n equals 4. Right, and so we have to be able to fit an integral number of half wavelengths in there, otherwise this will be forbidden. And so this will be allowed. Because it just keeps. And so we don't see quantization of energy until we get to very small objects, because with only very small objects are the wavelengths going to approach the dimensions of the object. And so if we look at a baseball, so we have a baseball leaving here and then arriving here. We look at how many half wavelengths there are. It's going to be very small compared to the baseball. And so the next allowed energy here is just going to be a hair faster. And a hair faster, well, that's allowed because, but if we look at an electron, the next allowed energy is not a hair faster. The next allowed energy would be a significant jump. And so what we're going to see here is an electron versus baseball, or both are quantized. The only difference is that the energy levels or the spacings here are so tightly spaced, it's essentially continuous. Whereas for an electron, the energy spacings are much larger gaps. As electrons approach higher and higher energies, we'll see the same thing happen though. Because, you know, at these lower energies, you'll see that there are big gaps. But as we go to higher and higher energies, the wavelengths get much smaller. And so when we're looking at the electron energies in the hydrogen atom, we go from 0 joules here at E infinity all the way down to E1, which is minus 2.179 times 10 to the minus 18 joules. But you know, the Bohr model was wrong. The Bohr model is wrong. Are these numbers wrong? The Bohr model's wrong. Are these numbers wrong? No, these numbers came from the experiments, and those were factual observations. And so the next allowed energy, E2 here, is going to be a big jump, right? Because we've got to do that. E3, E4. But between this energy and this energy, how many lines do I have to draw? An infinite number. So as we get to higher and higher energies, the spacings get so tightly spaced, it's pretty much a continuum up here. This can actually absorb more energy than this. An electron can absorb more energy. Well, how can it? Because the highest it can go is 0. Well, what happens is, if it absorbs more energy than this, it knocks off the electron and then kicks it off with velocity. And so it gives it a boot. So we're going to absorb more. Okay, the next thing we have to consider is the uncertainty principle. Or the Heisenberg uncertainty principle. Let's say Heisenberg uncertainty. This is Heisenberg. So what is the Heisenberg uncertainty principle? This is it here. Delta x times delta p. Delta x times delta p is greater than or equal to h over 4 pi. Delta x is the uncertainty in position. Delta p is uncertainty in the energy or momentum. This always has to be greater than h Planck's constant over 4 pi. And so there's inherent uncertainty for the electron. So if we locate or pinpoint the electron, if we pinpoint the electron, the uncertainty in the electron goes way down. The pinpoint electron in space, then, we've located the position of the electron. But if you locate the position of the electron, what's going to happen to the uncertainty in the energy? The uncertainty in the energy is going to go way up. And so the energy is uncertain. So what happens is this, energy for the electron, it's going to have a certain velocity, which means it's going a certain direction at a certain speed. And so if you try to observe an electron, how do you observe electrons? Well, we have to shine photons at those electrons. So a photon comes, and although it has no rest mass, it does have momentum. When the photon comes in, photon's h nu, hits the electron, it's going to change its velocity or direction, momentum. So this is going to be uncertain. You know, which direction was it headed, or where is it going? Because we hit it with a photon here, we pinpointed it, but we can't strike the same electron here necessarily. Or, you know, if we pinpoint the energy, that is, let's say pinpoint the energy of the electron, then what happens to its position? Well, the position is going to be uncertain. Position is uncertain. And so when we pinpoint the energy, we want to know the energy of the electron. The electron energy, well, let's say what's E2? E2 is going to be, I know what that is. E2 is just equal to minus R sub H over 2 squared. In other words, it's going to be minus R sub H over 4. Where R sub H is, well, this is just minus 2.179 times 10 to the minus 18 joules divided by 4. So we pinpointed the energy. Right? If we pinpoint the energy, what does it tell us about its position? Well, we pinpoint the energy, then the uncertainty in the position is going to go up. And so, are you going to know exactly where that electron is? No. You don't know exactly where the electron is. And so don't know where the electron is with certainty. Well, does that mean the electron can just be anywhere, you know? Well, you don't know where it is, but we use probability to describe electron position to give an idea where it might be. Probabilities are shown in different ways. You know, let's say we have a nucleus here, and we want to show the probability. One of the things we could do is, well, that electron isn't going to just be anywhere. It's most likely going to be close to the nucleus. We can show that using dots here. And then as we get farther from the nucleus, then the probability of finding that electron is going to go way down because the electron is less likely to be out there. And so when we go way out here, you know, then it's most likely an electron with this energy isn't going to be this far out. This is like the bird analogy, you know. The bird, have you heard the bird analogy for this would be, this is the nest, the bird's nest. Now, how far away is the bird going to travel from the nest? Well, it depends on the energy. If the bird just has the typical daily, let's say diet, then it's most likely going to be out in this region. Well, it's probably going to be closer to the nest, but as you get further from the nest, the probability is going to go down because it just doesn't have enough energy to be out there, right? And so this would be it. But where exactly is the bird going to be, let's say, 2 days from now? Are you going to be certain about that? No, but you're going to have some idea. Well, it should be in this region, right? It would be highly unlikely to be found out here because of the energy, correct? All right, let's say, well, this is what we call an electron density, or cloud, electron cloud. We can graph this, here. The nucleus is here, then probably the highest probability is close to the nucleus, and then it drops off. And as you get further and further away, it'll hit 0. I mean, there is a small probability it could be way out there, because how can you predict? The bird might actually fly pretty far from the nest. But the probability is low. All right, now if it's higher in energy, then the probability is probably going to be farther away from the nest. So higher energy could go quite a bit farther out. And so we can have different densities depending on that. And so what we do here is, what do we want to know more? Do we want to know more about the position of the electron at different times? Like, do we want to know more about where that bird is actually located in the neighborhood? And not know anything about its energy? This could be a high energy bird that just happens to be right here. Or it could be a low energy bird this is its terrain here. Do we want to know that, or do we want to know the bird's energy and then have some idea of the probability of finding it? What would you rather know? Or maybe, a little of both. Well, a little of both isn't very good. It isn't very useful. So let's know one or the other. So what would you rather know, the energy or the location, and know nothing about where the bird came from? The energy. And so that's exactly what we want. We want to know the energy of the electron. But if we know the energy of the electron with certainty, then its position has to be given by a density or cloud distribution. But the density or cloud distribution is not totally random. It's not like this cloud is going to span the entire universe. It depends on the energy, and we can get an idea of where that bird should be based on its energy. Correct? When we incorporate these two ideas, then we come up with a new model for the hydrogen atom. This is an uncertainty principle using waves. Wave packets. So we incorporate, what Bohr didn't do is he didn't incorporate the wave properties of an electron. But when you incorporate the wave properties of an electron, because people know about waves, and they know about waves, destructive, constructive, and other things. Particle in a box. Particle in a box would be an electron in a box. Electron in a box can hold only certain energies. All energies, other energies. If you're an electron stuck in a box, then you can have this energy, you can have this energy. But if you try to put in, let's say, 3/4 of wavelength, then it's going to be forbidden. So you can't sustain that. When we incorporate these ideas, then we end up with a new equation describing the physics of this. And so let's go on to this equation here. This is a particle in a one-dimensional, this is a particle in a three-dimensional box. So this equation, the particle in a three-dimensional box, looks very much like the equation that we're going to come up with here. That is this equation. This is the particle in a three-dimensional box, but it's using some symbols to shorten it here. Yeah. This equation is called the Schrödinger equation. And so when we have, quantized energy, we have, the de Broglie, we have the Heisenberg, and then we combine these into the physics and do the equation for this, we end up with the Schrödinger equation. The Schrödinger equation describes the electron in an atom. So we can get all the information of an electron in an atom from the Schrödinger equation. This is the Schrödinger equation. Yeah. Usually we use different symbols. Well, what is a description of an electron in an atom? Well, we're going to pinpoint the energies, right? And so we want the electron energies. Electron energies. That we're going to get from this. This E is the energy for the electron. And we also want the position of the electron. But the position of the electron is not going to be pinpointed. The position of the electron is going to be given by a probability function. This. And so electron energies and position probabilities. So the Heisenberg, the Schrödinger equation in its simplest form looks like this: H psi is equal to E psi. E, this is the energy. Psi, this is the answer to the Schrödinger equation. The Schrödinger equation tells us what are the allowed energies for the electron and the hydrogen atom, helium atom, whatever. And those allowed energies are going to pop out here. The energy, and interestingly enough, for the H atom, the energy is very simple. Energy, there are multiple allowed energies. In fact, there are an infinite number of allowed energies. And so when you get the answer here, you either solve it to a single answer or you solve it to an equation that answers it. And the equation that answers it is the energy for a hydrogen atom just depends on n. This is minus r sub h over n squared. And so we get this exact same energy equation as we got from Bohr by using the Schrödinger equation. Now the psi is interesting. The answer to the Schrödinger equation will be these three things. Now psi is what we call the wave function. And it's going to describe it. And psi is a wave function. This is called an orbital. And that's the answer. And so what we end up getting are orbitals. Now orbitals are going to have a distinct energy, E sub n. For all others, H atoms, for one electron species, we get this. En is equal to minus z rh over n squared. We have to add in the proton charge. For multi-electron, it turns out that energy is not a function on just one variable. Energy is a function on n and something called L, which we'll talk about later. And so for multi-electron, there are two variables that we have to know in order to figure out the energy. So an orbital is going to have a certain shape, and that's given by psi squared. Psi squared is called the probability function or probability for its position. And so psi squared is going to give us a shape to the orbital. Shaped orbital. For the hydrogen atom, the Schrodinger equation can be solved exactly. So let's take a look at this. When we solve the Schrodinger equation, since there are an infinite number of psi's, we use mathematical equations to describe it. So for the H atom, there are infinite answers. And for all atoms, there are infinite answers, infinite number of answers. And so infinite number of psi's. There are infinite number of psi's. How the heck are you going to figure them all out? Well, it turns out it's very easy to figure out because the answer is not a specific number or a specific value or a specific shape or whatever. The answers are going to be in terms of equations. And so it turns out that each psi depends on 3 variables, n, l, and m. These are the quantum numbers. N, L, and m. So each psi, well, n can only have certain values. So the values of n are allowed 1, 2, 3, etc., all the way to n equals infinity. Because if you try to plug in an n value that isn't one of these, it doesn't answer the Schrodinger equation. All other values fail. And they do not solve the Schrodinger equation. This is called the principal quantum number. The principal quantum number gives us an idea of the energy. That is, the higher the n, the greater the energy. L is called the angular momentum quantum number, or azimuthal quantum number. We'll just call it the angular momentum quantum number. L tells us a bit about the shape of the particular orbital, and that is the L values that are allowed are 0, 1, 2, ... all the way to a max of n minus 1. These kind of give us the shape of the particular orbital because an L equals 0, this is called an S orbital. And S orbitals have a spherical shape, but the S does not come from spherical. S actually came from spectroscopy. Spectroscopists notice a very sharp line. The biggest one was this one, which they call P. The P stands for principal. This is the principal peak in the spectrum. But this is a p orbital. And L equals 2, this is what we call the d orbital. And S, P, and D are going to have different shapes to them based on their angular momentum. Finally, the last quantum number, m, this is called the magnetic quantum number. The magnetic quantum number is going to vary. M equals all values from minus L to minus L plus 1, ... through 0, ... through L minus 1 to L plus L. And so let me just do an example of this. If M equals 2, if L equals 2, then M is going to equal minus 2, minus 1, 0, plus 1, plus 2. all of them. And so, but the magnetic quantum number tells us is the number and orientation. For example, when L is equal to 2, we're dealing with a d orbital. If we have a d orbital, then it turns out there are 5 d orbitals because there are 5 m quantum numbers. 1, 2, 3, 4, 5. And so this would mean 5 orbitals. And the orientations can be coded, you know, because a -2 versus a -1 can have a different orientation. So there are 5 d orbitals with different orientations. They're all the same energy, though. And so it's easy to determine. We aren't actually going to solve this, but for the hydrogen atom, the Schrodinger equation can be solved exactly. Exactly. And so here, the first allowed would be n equals 1. When n equals 1, then L can be 0. And so this, we have psi n equals 1, L equals 0, and n equals plus 0 to minus 0, so 0. And so this is what we call the psi 1, 0, 0 orbital, which is also equal to the psi 1s orbital, where n and L are shown here. And so the first allowed orbital is the 1s orbital. The energy we can calculate is just E1 is minus r sub h over n squared. Now when we go to the next allowed one will be n equals 2. When n equals 2, then we can have L equals 0, but we could also have L equals 1. Because we can go to maximum of n minus 1. When we have an L equals 1, then we have 3 m values. We have m equals 1, minus 1, m equals 0, and m equals plus 1. And so we end up with these orbitals here. And we call this one a psi 200 NLM, or a psi 2s orbital. Over here, this would be a psi 21 minus 1. This would be a psi 210. This is a psi 211. And so what we end up with are psi 2p, the orientations I got to double check, 2px, 2py, and a 2pz, you know, showing the orientation of the p along the x, along the y, and along the z. All these orbitals have the same energy, these 4 orbitals. And so when we have it here, we have E2, which is just minus r sub h over 2 squared. This is 4. Okay, now based on the mathematical pattern, we can generate, you know, all the orbitals for the hydrogen atom. And there's some other patterns here that you might start to recognize. When we go to n equals 3, then we could have an L equals 0. We could have an L equals 1. Let's do that up here. Running out of room. So if we go to n equals 3, then the possible L values, L equals 0, L equals 1, or L equals 2. We can't have an L equals 3 because that wouldn't solve the Schrodinger equation. It would be a violation of the Schrodinger equation. When L equals 0, m is equal to 0. When L equals 1, then m equals minus 1, m equals 0, and m equals plus 1. When L equals 2, m equals minus 2, m equals minus 1, m equals 0, m equals +1, m equals +2. And so all these orbitals, how many orbitals do we have here? Do you see how many orbitals we have? Count them up. All together, we have one orbital, one s orbital. This is a 3s orbital. This is a 3s orbital. We have 3 3p orbitals, and we have 5 3d orbitals. Do you see that? And so all together we have 4 plus 4, we have 8 orbitals. Is that right? No, 9 orbitals. We have 9 orbitals in total. And so do you see another mathematical pattern here? Do you see one more mathematical pattern that we can see when we're doing this? And that is, how many total orbitals are there at n equals 1? There's 1. How many total orbitals are there at n equals 2? 4. How many total orbitals are there at n equals 3? And so the pattern is that there are n squared orbitals for each n value. Okay. There are n squared orbitals for each n value. And so when I go up to n equals 10, how many orbitals are there going to be? 100. Can I figure them all out? Yeah, it's not difficult to figure them all out. We aren't going to do n equals 10. Let's do something easier. N equals 5. We can do that very fast because we don't have much time. If n equals 5, how many orbitals am I looking for? 25 orbitals. What are they? Well, at n equals 5, I'm going to have L equals 0, right? I'm going to have L equals 1, L equals 2, L equals 3, and then L equals 4. I can't have L equals 5. That would violate. And so in other words, I'm looking for S, P, D. What comes after D? F. What comes after F? What comes after F is an E orbital. And then I'll just go alphabetical. This is where we run out of things. Okay, so L equals 1, we have this. M can be -1, 0, +1. When L equals 2, M is -2, -1, 0, 1, 2. When L equals 3, M is -3, -2, -1, 0, 1, 2, 3. And then we're out of time, but when L equals 4, what are my M values? Actually, my M values are going to be -4, -3, -2, -1, 0, 1, 2, 3, 4. And so how many orbitals are L equals 4? Well, in the 5e, there are 1, 2, 3, 4, 5, 6, 7, 8, 9. Do you see a pattern? The pattern is for each L, there are 2L plus 1 orbitals. And so if L equals 4, they're going to be, well, 2 times 4 is 8 plus 1 is 9. They're going to be 9 orbitals. Okay. That's the other mathematical pattern. And so we could figure out the whole chart all the way up to infinity. It'll take you a long time, though.